Warm up for today, please pause and solve. Okay, so this says that a new headache remedy was given to a group of 25 subjects who had headaches. 4 hours after taking the new remedy, 20 of the subjects reported that their headaches had disappeared. From this information, you can conclude. I would say the answer to this is option C. Nothing. We cannot conclude anything. The reason has nothing to do with the sample size. It has to do with the fact that I don't have a control group here. I have nothing to compare it to. Usually when I get a headache, even if I don't take anything, 4 hours later, that headache's going to be gone. Okay, headaches don't last forever. So are these people's headaches gone because of the headache remedy, or are they gone because they would have been gone anyway? And we don't know because we don't have a group to compare it to. Okay, so hopefully by now, we talked about this a lot in Chapter 3, you know that correlation is not the same thing as causation. Just because two variables are strongly associated does not mean that one causes the other. What is it that constitutes good evidence for causation? We need a well-designed experiment. That is the only way to conclude causation. This is really, really important. I can almost promise that this is going to be a multiple choice question on the AP exam in some form or another. The only way to conclude that one thing causes another is with an experiment, not an observational study. Must be an experiment. So, in fact, there are 3 ways that we can explain a correlation or an association between two variables. Okay? The first is causation. That is a possibility. X causes Y. Now, even if we do have a causal relationship between two variables, it may not be the only explanation. There have been a lot of studies about, let's say, the body mass index of women and the body mass index of their daughters. Okay? And we could say that those are linked genetically. Okay, you have a certain genetic predisposition for a certain body type, and you get that from your parents. However, we also have nature to consider. If, my mom eats really healthy foods while I'm little and she exercises and things like that, there's a good chance that I'm going to pick up on those good habits and have good health and eating habits like that. Whereas if my mom eats junk food and doesn't take care of her body, then there's a good chance that I'm going to do that as well. So do we have similar body types because we're similar genetically, or because I learned my habits from her? Okay, so it could be causation, but it could also be something else in addition. Also, clear causal relationships may not generalize to other situations. Medical experiments on rats, for example, are a lot of times used to, in experiments. But that doesn't mean that those results are going to generalize to other situations involving people or involving rats that aren't in a laboratory. All right. However, still, the best evidence for causation is going to come from experiments, controlling the explanatory variable and observing the response. If it's not causation, it may be something called common response. This is when we have a lurking variable that causes changes in both X and Y. For example, it's been shown that there is a high association, a strong correlation, between SAT scores and the grades that someone receives in college. Okay? Generally speaking, someone with low SAT scores does not receive awesome grades in college, and someone with high SAT scores does. But does that mean your SAT score itself causes you to get certain grades? No. I would say we have these lurking variables like intelligence, like work ethic, like study habits that are causing both of these things. They're causing a certain SAT score and they're causing your grades in college. So in common response, I have two variables that are responding in a common way to some other variable that's not the explanatory or the response. And the third explanation is called confounding. Okay? Two variables are confounded when their effects on a response variable cannot be distinguished from each other. Usually, the two variables that are confounded, One is an explanatory variable and the other is a lurking variable. Confounded just means like confused or mixed up. So basically, I'm not sure if it's this variable, that variable, or some combination of both. The example I talked about at the very beginning about the body mass index of mothers and the body mass index of their daughters would be an example of confounding variables. The influence of genetics and heredity gets mixed up with the influence of habits. Okay, we don't know which is causing the relationship. They're too difficult to separate out. Here are a few more examples of confounding. A soccer coach wanted to improve the team's playing ability, so he had them run 2 miles a day. At the same time, the players decided to take vitamins. In 2 weeks, the team was playing noticeably better, but the coach and the players didn't know if it was from running or from the vitamins. So from the coach's standpoint, the running is the explanatory, and the vitamins are this confounding variable or this lurking variable that gets in the way of that relationship. Okay, so the vitamins are what confounds the results that the coach is trying to see. Okay, those two variables of running and taking vitamins got confounded. I don't know which is causing the better playing. Another example, when Susan is stressed, she gets muscle cramps. However, when she's stressed, she also drinks lots of coffee and she loses sleep. So I can't tell whether her muscle cramps are because of stress, because of coffee, right? Caffeine dehydrates you and it can cause cramps, or because of the lack of sleep. Honestly, it's probably some combination. So she may want the stress to be that explanatory variable. But we have these lurking variables of coffee and sleep loss that are confounding that relationship. So I want you to look at these 3 diagrams and decide which of these is causation, which of these is common response, and which of these is confounding. And in each of these, the dotted line just means that there is an association between X and Y, and then the rest shows whether it's causation, common response, or confounding. So pause and figure it out. Okay, hopefully you got that this first one is causation. X is directly causing Y. There's nothing getting in the way. This one down here is common response. I have this third variable, Z, that is causing changes in both X and Y. And then this guy over here is confounding. Is X causing Y? Is Z causing Y? Is it some combination? I don't know. So back to our original question, how can we establish causation? And if possible, the answer is that we design a good experiment. This leads me to something called the 3 basic principles of experimental design. And they are control, replication, and randomization. We must have all 3 of them in order for my experiment to be well designed. Okay, these are 3 really, really important vocab words that they really do test you on the AP exam. So here's the first one, control. Control is when we try to eliminate the confounding effects of lurking variables. And the way we do that is minimizing the variability in the way that experimental units are obtained and treated. In other words, I want everything to be equal except for the imposed treatment. This is not necessarily the same thing as having a control group. What this means is, say I'm testing 2 different types of fertilizers on plants, okay? In order to have control, everything else about the plants needs to be as similar as possible. I want them to be the same type of plant. I want them to be in the same soil. I want them to be receiving the same sunlight. I want them to be receiving the same amount of water and the same quality of water. I want everything else to be the same except for the treatments. That way, any differences in the response can be attributed to differences in the treatments. I know that if one set of plants grows better, it's because of the fertilizer that I used, or whatever it is that I said, not because of differences in water or differences in shade. That's control. This brings up an important phenomenon called the placebo effect. Those of you who have taken psychology have heard of this before. The placebo effect is that often people feel better if they're sick. They feel better because they think that they should feel better because they're receiving some kind of medical care. Okay, so a lot of times when they test a new procedure or they test a new drug, the two groups that we're comparing are the group receiving the drug and the group receiving a placebo. They think they're getting an actual medical treatment, but really they're getting something that would have no medical effect on them whatsoever, like a sugar pill. Okay, so if I'm testing some new headache medication, maybe I give half of the people this new headache medication and I give the other half a placebo. Then maybe 30 minutes later, I look and see if there's a significant difference between the headache relief that the people who received the drug experience and the headache relief that the people who received the placebo experience, okay? If there's no difference, then the drug's not really doing much, and these people would have felt better anyway, either because of the passage of time or because they think they should feel better because they took something. For me, a lot of the time when I have a headache, if I take something, I kind of feel better right away because I stop thinking about the headache because I know it's about to go away because I took something. All right. So what we need to do here to counteract the placebo effect is make everything else the same except one group gets the actual medical treatment and the other group gets some placebo treatment. Okay? So basically, the simplest form of control is comparing several treatments underneath the same environmental conditions, so with everything else the same. The second principle of experimental design is replication. In any experiment, even if I have all the control in the world, we have chance variability among experimental units. Even if I make everything else the same, no two humans are actually the same. No two trees are the same. No two bunny rabbits are the same. All right? And so because of that, if I assign each treatment to only one experimental unit, we cannot tell if the differences in response are due to differences in the treatment or because of natural variability. Back to the plant example I used with control, if I'm testing the fertilizer, two different fertilizers, if I only have one plant getting one fertilizer and the other plant getting the other fertilizer, if one grows better, I don't know if it's because that was just a better, healthier plant or if it's because of the fertilizer. So if I see units within a group respond similarly, it's more likely that the response is due to the treatment rather than due to this chance variation among experimental units. If I have 50 plants receiving one fertilizer and 50 plants receiving the other, and the 50 plants that receive the new fancy fertilizer grow big and healthy and are awesome, and the 50 plants receiving the old fertilizer die in a day, then I think, there is a difference between these two fertilizers, okay? I can make that conclusion much more strongly than if there were just one plant in each treatment group. So replication refers to using enough subjects to reduce the impact of that chance variation. It doesn't eliminate the variation, it just reduces the impact that it has. It reduces its role, and it increases the sensitivity of our experiment to differences between treatments. I want to be clear here. Replication doesn't mean doing the experiment over again. It does not. It means I have multiple experimental units in each treatment group. The final principle of experimental design is randomization. Randomization means I have to randomly assign experimental units to the treatments. Who gets which treatment needs to be randomized. And the acronym I have for you is RAT. We need to randomly allocate our treatments. Just like in surveys and sampling, I needed to randomly select my sample. Same idea here, except I need to randomly allocate who gets which treatment. I don't get to choose certain individuals to go into the drug group and certain individuals to go into the placebo group. That's not fair. It needs to be random. So like I said, just with selecting samples, we have to rely on chance to make a treatment assignment that doesn't depend on any characteristic of the experimental units and does not rely on the judgment of the experimenter in any way whatsoever. Relying on chance helps us ensure that external influences play equally in all of the groups. So when we randomize, differences in the response variable are either because of the explanatory variable, which is what we're hoping to show, or due to chance alone. And our goal is to observe an effect that's so large that it wouldn't really happen by chance. And this is called statistical significance. If we see a result that is so big, a difference between, for example, the treatment group and the placebo group that's so big that it wouldn't happen by chance, that result is statistically significant, unlikely to happen by chance. We're going to talk about this a lot more later. That's pretty much what inference is all about. So if that didn't quite make sense yet, that's okay. So to summarize, we need to control the effects of lurking variables by comparing different treatments under the same conditions. We need to replicate each treatment on many units to reduce the effects of chance variation. And we need to randomly assign treatments to the individuals. Here's homework assignment number 3. There are a couple homework questions that ask about diagramming experiments. I didn't actually talk about this, but I think you could look at this experiment diagram and figure it out. The first thing I do is randomly allocate students to 2 different groups, group 1 with 20 students and group 2 with 20 students. I give each group their treatment, and then at the end I compare responses between the 2 groups. Here's another one. This time I have 6 groups, so I randomly allocate individuals into the 6 groups. Each group gets their treatment, and then they all come back together and I compare the responses. So let me put this back up on the homework slide.